All right, thanks everyone. All right, my name is Dr. Martha Lenio. I work for a company called, I guess, Solvest now. It was High Latitude Energy Consulting. I'll introduce both. So Solvest has been around since I think 2014 or 2015. Oh, it says founded in 2012. Okay. It's based in Whitehorse, Yukon. They employ over 60 people across Canada, mostly in the north. It's the largest renewable energy company in northern Canada, and they own, operate, and build solar power plants. So they're started off, and like expertise is largely around solar. In 2022, they split off this company, High Latitude Energy Consulting, mostly to look at feasibility of larger scale, community scale feasibility studies to help communities get off diesel and onto renewable energy across the north. It's this space that's really challenging and they want really expertise in. So they started that in 2022 and hired me to help start that off. Yeah, and our aim is to provide clients with like the confidence to make renewable energy investment decisions and drive public projects and stuff, largely again in Canada's northern remote communities. I'm personally based in Khalid. So this presentation will be maybe like a little bit shorter than some of the other ones, but a little bit more focused on the modeling work that goes into helping to make these decisions. And also from the perspective of a small consulting company where we're like, 5 or 6 people, Homer is by far like, the baseline standard for microgrid modeling, I'd say, right now. But there are some challenges that come with that. Number one is that it's very expensive. It's about $5,000 a seat. So if we need like 3 seats, that's $15,000. There's a comment like, you need $15,000 to do something, we can't do it. So we're like, this is a lot of overhead for our clients and for us. So we're looking for more affordable ways of doing microgrid modeling. I tend to go to the IEEE Photovoltaic Specialist Conference every year, and there's always great stuff on grid integration. So I knew there were some good Python-based tools out there, so we started looking into that and came across all the ones that you can see there that were not as good as PGM, which Anthony developed here at UVic. So we started looking at that more. Yeah, some of the other weird disadvantages of Homer is like, again, you have to pay for each add-on module. So if we're looking at like hydrogen for communities, that was like an extra add-on. If we're looking at tidal for communities, that's an extra add-on. If we want to do a 30-year forecast, that's an extra add-on. So it gets expensive pretty quickly. It's a bit of a complex interface. It's a bit of a black box. Some weird things would happen, especially when we were doing things like hydrogen, like it would put in a hydrogen fuel cell and no electrolyzer. We're like, why are you doing that, Homer? Like, we need both pieces in this system. So there are just these kind of weird things that would crop up with Homer. And we're like, we wanted more control over the dispatch as well of assets. So we started looking into different programs, came across PGM, and have been working closely with UVic. This presentation is also just kind of to get us thinking about modeling and gaps and what we want and what we need in order to communicate results. One of the things with PGM is really, really great, but just gave you folders full of data. So my colleague Bezad, who may hop online and be able to answer more technical questions later today, implemented this dashboard. So you can very easily see the results. You can zoom in on results. You can turn things on and off, see when your diesel is dispatching, when your solar is dispatching, and kind of zoom in on things as well. It'll give you, there's different tabs so you can get the model summary and different, emissions, things like that. So it all kind of plots it out. You can also see down in here, there's operation mode. So you can also look and see when it's, this one was for QEC, I think, Kulik Energy Corporation, one of their grids. And you can see when it's in like mode A or mode B, which is like diesel on or diesel off. So you can see at the different times of year when we're actually operating diesel off. So that's just one of the things that we did to make it more accessible. one of my suggestions, I also come from kind of like, I'm a mechanical engineer by trade, and also do a lot of energy efficiency and building stuff. So I guess one of the things for me that's challenging is I'm not much of a coder. So to go in and start playing around with C++ or Python is a bit of a barrier for me. But I just wanted to share, maybe UVic, you have a summer student at some point, you want to think about interface, make this sort of thing more accessible. This is Energy Plus, also like Python-based program for doing energy modeling, but it just kind of walks you through building the whole thing out. So, you know, you can put in your files, and then it kind of, I just have the schedule here. So you've got your, 24-hour day, and I can do my schedule for temperature, for cooling, for surface water heat. And it can be Monday to Friday, Saturday, Sunday. So I can define, it just walks me through creating each of these objects. I don't need to have to code anymore. So it's like, this would be a great thing. I'm just going to put that up there and see if, you have a summer student sometime that wants to do a project.
I've leveled up my graphical interface programming a bit, so it's coming.
Woohoo. One of the other great things, ACET is an excellent programmer, so he does a lot of this kind of stuff. One of the things is with PGM that we really loved is that it is very flexible. So we were able to implement different dispatch protocols, work with Anthony on getting that kind of implemented. For diesel and renewable-based microgrids, we were given an interesting, and one of the great things about Highlight is we can take on like really interesting projects sometimes. So we were asked, can heat batteries help with grid stability and increase renewable energy uptake and or reduce greenhouse gas emissions this was for a northern hydro-based grid. So it's a bit of a larger based grid, the example I'm going to show. So we actually took PGM and we took the lithium ion battery kind of energy storage class or object or whatever it is, and adapted that to model a heat battery instead of a lithium ion battery. So just kind of changed its characteristics, built our own energy storage asset. So some of the key changes to the code were there, new class, matching efficiency losses to what a heat battery is rather than a lithium ion, conversions between heat and electricity. This is just some of the code that I pulled from ACET. It was very, I think the key one is just way down here at the bottom. The loss rate it says lithium ion, this is really a thermal energy storage, but it loses 3% heat per day. So making sure that was captured, that kind of heat loss and efficiency loss there. So again, we can go into the code. We know what all the equations are. We can adapt them to our needs. And then we didn't really use PGM for the dispatch. ACET again wrote his own dispatch strategy, so he wanted me to emphasize that this is it. But you can kind of see at the top is the existing grid with its load and how it's getting serviced by wind, solar, hydro, fixed diesel, rental diesels. I believe on this grid there's 31 rental diesels or something needed to hit those peaks, those light gray peaks in the winter months. And the only excess is, I'm going to point to this lower graph as opposed to the upper graph, but you can see the load is this dotted graph. Everything above that is curtailed or excess energy from your hydro and solar and wind across the summer months. So we are able to say capture that in the heat battery and then dispatch it in the winter months and save them from and I think in this case it was saving the cost of 7 diesel rental generators. So again, we can share that with the utility. They can make their own cost assumptions on that. We can give them some indication, but they're going to know their costs a bit better than we will. But that was just like one example of how flexible PGM was for us, how we've been able to kind of take that, run with it, and look at different grid problems and different ways of solving them. So this one, again, this was for grid support. So this was case was taking excess electricity from the grid, saving it in a heat battery, and then converting it back to electricity to support the grid. not the most efficient, probably, way of using your heat batteries. So that we were also able to look at if there were a district heating system servicing buildings, would we be able to take that heat from the heat battery and dump it back into a district heating system as needed, especially in, let's say, I'll read the actual question. So can heat batteries help with maintaining a district heating system that currently relies on waste heat from a diesel genset and allow it to go diesel off as renewable energy is added? So in Nunavut, for example, we have diesel, all of the communities are diesel based. Many of the communities also have district heating systems where, including Santa Kilowak, which is a current community getting a wind energy project, they have district heating systems where the waste heat from the diesel is supplying heat to the school and the health facility and helps with costs there. If we put in a wind turbine, which is able to meet, 75% of the community's energy needs, is going to turn off the diesel gensets a fair bit of time, including in the winter or in the shoulder seasons. How do we keep those buildings warm? How do we keep that district heating system running? So the question was, can we, again, capture excess heat, store it in a heat battery, and feed that back into the district heating system when it's needed? So we were again able to, again, we had our own dispatch for this that BayZad created, but we were able to like adapt the diesel modules in PGM to be more like boilers. They use the same fuel supply, and we're going to be, I think they had the same dispatch. I don't know. I'll have to talk to BayZad about how we actually implemented, but the heat coming off the diesel gensets for the district heating system, but it was similar to the diesel. The boilers are kind of similar to the diesel because they're on a dispatch, similar to the electric grid. The curtailed clean energy, again, we captured that in the thermal energy storage system. And again, we used the modified lithium ion module, but supplying energy to a district heating system rather than the grid. We also have a different load need. So this was pulled from a district heating report. And the gray is the amount of heating needed. So that's your heat demand in terms of kilowatts. And then the blue is, this was like an existing district heating system. And then in the top graph. And the red is the number of days or the times when the heat load was not being met by the district heating system. So they had to maybe rely on backup boilers in the buildings. This bottom one was like, if they expand their district heating system, now we have more days where the heating is not met. And then we could introduce extra renewable energy to the system and see how we can better meet the need. Sorry, if that's not clear, I can answer questions. But yeah, that's again just one application that we'd be able to modify PGM to help us with different modeling needs in remote grids and kind of adapt it to different types of energy storage and have control on the dispatch and yeah, get some initial answers on what will actually work in this system. So thank you guys for having me here today. And yeah, I'll take questions, and if I can't answer them, my colleague BayZad will probably be able to. All right, yeah, go ahead.
Can you bring me along and describe exactly quickly how a heat battery works?
How a heat battery works?
Yeah, use small words.
Okay. So what a heat battery looks like is a large thermal mass. So like sand or concrete or something like that, really well insulated. And then probably with some kind of like embedded glycol loop or something. So it's a little bit like geothermal, but like we've designed it. So what you use to heat that kind of heat battery could be electricity. That's what we're looking at with a lot of renewable penetration. If you can't put it anywhere else, may as well put it to heat. And then it's dispatchable for when you need the heat. Does that?
Through
Yeah, like a heat exchange system. So it could be either, so you could use that heat either directly as heat and have it running again through probably some kind of glycol loop to buildings, or you can use that to create steam or something and generate it back into electricity, but you're going to have losses again associated with that. So, yeah. Oh, we're back in.
So yeah, I love the idea of a thermal battery and some of these options as well. For the ACET project. I'm curious, like the costs of that extra infrastructure, especially when you think about using excess heat, storing it, and distributing it to the network. Like, have you seen any cases in the communities where that level of additional investment actually?
I think, yeah, that's a hard one to say. Like I haven't seen it in so many remote communities. It's getting uptake in Scandinavian countries. So it is interesting to see like what they do with it in Finland or something. And then there's a lot of like building level uses for this, more like, so I think there's a brewery in Scotland. There's a very, I don't know if you guys know the Okotoks project in Alberta. It's like a 90% solar powered community, and one was like they built like a big kind of like geothermal heat battery storage, and they collected solar thermal energy from the roofs all over the summer and held it in this big heat sink at the end of this row of houses, and then used that to heat the homes again in the winter. That one was, one of the problems is it was very much custom designed, and then once things started breaking, they couldn't fix it on it. So I don't know, with some of these companies are coming up with like kind of like turnkey heat batteries that like, it's either in like a sea can or some kind of containerized solution. It uses local rocks or sand or whatever your local materials are. So there's like hopefully not too much in terms of shipping costs for it. It is kind of low tech. So, maybe with that kind of like, instead of it being like a custom design job from, a whole bunch of engineering firms and then like various pumps and controls disappear or something over time and you can't quite replace everything properly. Hopefully with like something a bit more turnkey, that would be addressed. Yeah.
Sure. Is there...
Yeah, I forget, there's somebody else.
Go ahead first.
Okay, sorry.
Sure. Yeah. I don't want to jump in. That's okay. Yeah, with these heat batteries, I'm curious if I'm recalling my Rankine cycle correctly. It's driven by like the difference in temperature. So I'm wondering if you're using waste heat from diesel, what kinds of temperatures can you obtain with something like a heat battery? And through maybe like concentrated solar or something like that, you could maybe get higher temperatures. And then how does that dictate what fluid you're using and what your efficiency is?
These are all really great questions that I don't have all the answers to right now. But yeah, with the heat battery, I'm not sure how it, like some of them, I mean, we looked at a whole bunch. They can get to quite high temperatures. I can't recall exactly how they're attaining all of those very high temperatures, if it's all like mostly waste heat from industrial processes in that specific use case, or if it's more like what we're seeing with district heating systems where it's just the waste heat off the diesel generators. So I can't say off the top of my head what the max temperature we can achieve what that is, but I do know that they can go quite high, like into like the 1,000 degrees Celsius type. So that it's a pretty broad technology as well. So
kind of similar question. Yeah, I was wondering what the temperature of these batteries gets up to. Also, how do you actually measure the storage capacity? Is it like in megawatt hours, gigajoules, or? And third, what is the cost to actually deploy one of these in, say, dollars per megawatt hour?
That is a good question that we have I know we have a whole report on that for our client. I can't remember the exact numbers, but I can look up the numbers maybe over lunch or something. But again, it really depends on the material, what the temperatures you can go to. So it can be like everything like sand or concrete. There was also very fancy materials where it was like concrete with like embedded aluminum beads that could like melt, and then you've got some phase change going on in there as well. So there are, similar to like batteries with the thermal energy storage systems, there's actually a really wide range of materials with a really wide range of like underlying thermodynamic processes are supporting those temperatures. Yeah, it's really quite interesting. But yeah. Dave, and then
Martha,
yeah.
I remember Yukon Conservation Society and Eric did the ETS study.
Yeah.
What was the status of that? Did that energy storage?
Yeah.
Basically something fireplace bricks.
Yeah, so on like this more simple end of thermal energy storage, there's that project. We did interview with them. They weren't really ready to release their results yet. One of the challenges was, I think, the weight of the brick, these like brick furnaces or the brick thermal energy storage things, and the space that they take up in homes. But otherwise, I think it worked pretty well. One of the use cases too is like, I think it's called Giganak in Alaska. They have a really interesting project that's, they had like wind energy, bunch of excess energy that they couldn't use. So they put these thermal energy storage, just like basically ceramic stoves in the homes of elders, and had it like radio controlled to whenever there's excess wind to heat the ceramic stoves of these thermal energy storage units in elders' homes. And anecdotally, elders were saying like, we used to use like, have to fill up our fuel tank every 2 weeks. Now we only have to fill it up every 6 weeks. So at a household level, that's the, recovering that. It would be really great to do that again, like, yeah, in remote communities, and it's very expensive to heat homes. So as, we develop these microgrid projects, kind of keeping in mind this like, well, that waste energy, it could be an opportunity to electrify something else and maybe have a reduced rate.
Yeah, we have a report, we can send it out. We did the technical analysis for that project, and I have an ETS unit in my house, so if you want personal and showable evidence of how it works, I'm happy to share. Of course, they're electric from storage.
Out there and then.
Yeah, so about the whole permanent storage project, my background is, well, I'm in a research group at home called permanent storage. We do like assess storage using different type of technologies. And it's actually maybe that was called microgrid, but it's actually interesting to see how much impact these type of permanent storage can have on an electric grid. Their estimates that Switzerland will have 5 terawatt hours of electricity lag in 2050, just because consumption is rising. Just by implementing seasonal permanent storage with our maybe between 17 and 20 degrees of operating temperatures, we can estimate like 2 terawatt hours is just built up with by implementing storages. So we have to almost 40% of the lag is just done by thermal storage. Yeah, I don't know, maybe if someone wants to talk a bit more about storage, just want to point it out, my background there. And the effect of these storages in these systems having the same, just figure out storing waste heat and have an electricity benefit from the grid stability and stuff.
Does anyone got any, sorry.
Oh, maybe Marianne.
I was going to not talk about energy storage at all, so if you're going to.
Yeah.
Oh no, that's like data centers are crazy. We demand water to take to cool.
Yeah.
So we're working with a couple of folks that do that, but that being huge.
But it's save our water.
Well, you're gonna use all that waste and heat for good, right?
Yeah. Yeah.
I think you're gonna like Pascal's presentation. He's about to give a kind of overview of storage technologies for remote settings. So maybe let's get there. We all can understand what he has to say.
Mary's question first.
Yeah. Question first. I also had the benefit of working with my guide and operator and stuff. I'm wondering, sort of from a private sector scenario, how do you decide when to bring on new microgrid modeling software and investing in that like fairly steep learning curve and to the approach that it needs to make that sort of a worthwhile exercise?
Yeah, that's a good question. When it was like highlighted to energy consulting, and I was a boss. Michael Schultz's benefit too, like we had like a professional development basically fund. It was like you could spend 5% on professional development or something. So we kind of like worked that out into like hourly commitment. It's like, okay, if we had again, we're a small company working in remote environments, but we also want to keep ourselves like kind of at the cutting edge and to give ourselves that competitive advantage. So we kind of said like, this percentage or hours per week or something on professional development, and also had just like we call them foundation projects. So it's like, okay, like your foundation project is like just researching what options we have out there in terms of energy modeling tools. Can we find something that would serve our needs better than Homer right now? Even if we like maintain one seat of Homer, because that's what everybody uses, just to validate the results and send it to other people, that still saves us $10,000. So it's like, Bezos not the Homer modeler, but if everyone else wants to model, give a first pass, we're going to use this other program. So it's just like, I guess, our thinking and approach to it, and then you have to just on a case by case, like we'd say, like, what are we spending a lot of money on? What is not, or what are the gaps? What's not serving our need? Like, are we able to model in Homer what's going to be the reality with a Kulik Energy Corporation grid? Is that serving our needs, or do we want to get more detailed? So that was kind of where we came up with that argument. Yeah.
Not a question, just a comment. I'm new to different microgrid modeling tools. I used Homer like twice a long time ago. To hear you say that you actually use Anthony's tool, I have that right, like developed at IESVic.
Yeah, well, we will use that tool for various, like, as he's like, I don't know how we would have done that thermal energy storage project
That's amazing.
With Homer, really. So just having been working with Anthony gave us kind of like, well, I'm sure there are other modeling programs out there for thermal stuff specifically, probably in the mechanical world, but we're like, we can also kind of adapt this to our needs to look at how we could support the grid. Yeah.
That's awesome.
Quick question, quick comment. Share the EPS report to both of you. If anybody else wants it, I'd be happy to forward it along as well for the electric storage. Second is a question. In the Yukon, I believe the utilities, the regulation is that the utilities cannot sell heat. So does this report consider that where utilities might not be able to see it as a battery because once it's in the heat, they can't necessarily sell it back unless there's an organic rank, like a turbine or something of the sort?
This is a great question about like ancillary services and how we regulate utilities and things. Like in Nunavut, our utility does sell the heat from there. They own all the district heating systems, and we sell the heat. I'm on the board of QEC as well. I did have like kind of a question for like the hydro EC and ATCO electric. So like one of the things I see, this can be like, I don't know when this will be a discussion, but when we get our capital plan presented to us at the utility, there's no consideration for the ongoing operation costs. It's just like, this is the capital we need to build a new power plant. And then I don't see like a net present value or a levelized cost of electricity. And I don't know if that's just the way public utilities are regulated across Canada. We're not allowed to look at that. But I'll also say we spend between $60 and $90 million on diesel a year or something like that. So it would be really great if we could start incorporating. So I'm just going to put that out there if like Norm or I forget your name from Greg have ideas on how we could better improve our capital planning at the utility level. That would be great. Yeah. Cool. All right. Thanks, everyone.